Okay, well, welcome everybody to this really special occasion where we have Mike Wallace um, to give us an informal survey of uh, atmospheric dynamics without equations, but how they're manifest in everyday, weather and satellite data, and just should be a real pleasure. Um, so Mike is very well known, really a pillar of modern atmospheric general circulation dynamics. I think all of us in this room and online are, grateful for his legacy. He's taught us so much about the real world and how it works. So I don't want to say too much at all, but Mike was my PhD advisor back in the 1980s. So I still feel like a little PhD student here introducing him. But I'm so grateful to continue to get to engage with Mike. Just before coming here, we were talking about, I was asking Mike when he had first come to NCAR. And it turns out he had come first as a graduate student in 1965. He was a graduate student at MIT at the time. And this was before the Mesa Lab came into existence. So he goes back farther than just about anybody in this room. And I think he knew Walt Roberts. And when he first came here to NCAR, I think he engaged with Raul Madden and Paul Julian and just these, names that are forever crystallized for us in terms of their important contributions. So Mike, as I said, has taught us so much about atmospheric dynamics, but I would say a hallmark of Mike's approach is really to emphasize intuitive understanding, conceptual understanding. But of course, equations are also underlie what you work on. So there's a new textbook that Mike Wallace with Dave Battisti, Dave Thompson, and Dennis Hartman have just published. And this is the work that Mike has done during his, quote, retirement. And I think he has many, many more projects in the coming years. So Mike is still very, very active. So I think today we will hear or see actually some of what's not in the book, but it is a collection of animations of atmospheric phenomena and their dynamics. So this will be very informal. Please feel free to just, interrupt, ask questions during the talk or afterward. And Mike will be spending the day here, and we'll have some time to talk individually with people. We'll eat lunch in the cafeteria or maybe outside if the weather holds up. So I think that's all I wanted to say. I'm sure I've forgotten some things, but please give Mike a big hand, a really special moment to have him back at the Mesa Lab. All right.
There. So, well, thank you, Clara, for that very, very nice introduction. I want to repeat Clara's invitation to interrupt at any time. The more informal we can make this, the better. And hopefully you will have some questions or comments along the way. So for me, this is like a trip down memory lane, seeing, in fact, even having some surprises of seeing people like Raul Madden here this morning, who I didn't realize was in town, and already seen a few other old friends. It's really does take me back many years, and in way of this particular seminar, there are kind of two events back around 1968 that are kind of early examples of animations that sort of tickled my brain in terms of thinking about phenomena. And well, one, just on a purely inspirational level, was in the NCAR cafeteria about 1968. And Walt Roberts loved to expose people to kind of the intersection between science and art. And he occasionally would have programs at lunchtime that were aired right in the cafeteria, and he had a big screen, and he got this video. This was before the days of online videos. This must have been a film that he showed with it was the performance of Vaughan Williams's Rhapsody, or on a theme of Thomas Tallis, and it was set against music of clouds and other natural phenomena, and it's just such a beautiful combination that really I was really touched by it. And the other, a little closer to my own interest, was this guy, Vern Sumi, who was, I think, one of my, several of my mentors, who at the time, circa 1968, was very much engaged in making the case for having geostationary satellites from which you could generate animations of clouds with something like a 10-minute resolution. But they didn't yet exist at this time. All there was polar orbiting satellites. And Vern had taken a bunch of these pictures, visible imagery on successive days, and put them together and showed them in rapid fire on the old slide projector. And it looked like an animation, and we could see the easterly waves marching westward across the tropics. And that was the inspiration for me to with students, C.P. Chang and others, to make these essentially, you would call them Hofmüller diagrams now, that were taken from the imagery from the polar orbiters and just arranged as strips on a page so that you could see this in a still image. And I think this is important, seeing that it was really the animation, or it was a poor man's animation that Sumi produced, that caused or enabled me to see the structure in the time, space-time domain for these moving waves. So Sumi eventually got the geostationary satellites that he wanted, or just a year or two later, and a lot of the imagery I'm going to show today is from those satellites. So a few words about the animations library. This was produced for the purpose of supplementing the textbook, and though there's no mention of it in the printed text, online you can find a link to the library, and Clara will be circulating a link as well. And so the library consists of a table of contents with little postage stamp views of these respective videos. There's about 120 of them now, and I'm hoping that we'll be able to grow this slowly, and hoping that some of you in this room may be contributing some, and also contributing to critiquing the descriptions of some of them that we have already, to be sure that they're as informative as possible. So I'm going to, for this talk, I'm just going to show you a series of examples And the first is from Isaac Held, and it's what he refers to as the fruit fly of general circulation models, just a pure dynamical core. And it starts from a state of rest with rotation and differential heating. We're seeing here the field of surface air temperature. The warm-cold scale is obvious. You'll see the temperature gradient build up, and then baroclinic instability will break out. And here, starting to see it, and then the rest of the video goes on pretty much in the same vein. Here we see the kind of the first example of how the general circulation starts from a state of rest. Well, to see these baroclinic waves in more detail, another, in this case, pair of animations that was made by John Methven at the University of Reading, and it's also with a dry dynamical core model, and we're seeing animations of the life cycle of baroclinic waves and the two forms of them, the life cycle 1 and life cycle 2, that develop depending upon the barotropic shear of the westerly current that the waves develop in. And I'm going to try to get these to start at the same time. And so we see in this case where the color is surface air temperature and the contours are sea level pressure. And we'll go through several cycles here. You can see the waves in the early stages are quite linear looking, and then they develop quite nonlinear features, fronts, and the structure is quite different. In the LC1, the cold frontal structure is emphasized. We see the cold front and the narrow band of warm air ahead of it. In the LC2, the warm front structure is emphasized, and it winds up into a much tighter spiral before you start to lose the structure.
Which one has more barotropic shear?
The LC2, to get LC2, you need finite more than zero cyclonic shear. And in the absence of any shear or presence of any anticyclonic shear, you'll get LC1. And work of Dennis Hartman and one of his students, Peter Zurcher, shows that the value of it, the transition between the two is discrete. There's a certain level of shear that it's all one or the other. There's no mix. But in nature, there is a mix because in nature, the waves develop in complex flows that may have cyclonic shear upstream and anticyclonic downstream and vice versa. So it isn't always so easy to classify the real phenomena. In fact, we'll get a little taste of that here. This is NOAA imagery, and actually what we're seeing here is precipitable water, which is giving a good indication of the vertical velocity field. And so that shows the fronts very nicely. Whoops, sorry. See. So this was a remarkable sequence of systems coming down the west coast here, and they look rather like LC1. And that just happens to be the prevailing flow during this time. So the baroclinic waves are really interesting to look at in all different kinds of imagery. And this is the precipitable water is one example. And I'm going to show you the next two animations are from the NASA GEOS model, which is very, very high resolution, in which they have a simulated cloud field. And whoops. Yeah. So over the United States, and this takes us through, this is late winter, and I think one of these systems is a big snowstorm along the east coast of the United States. We can see the shallow convection over the Gulf Stream behind the cold fronts. And the diurnal cycle in this is a bit overdone. It isn't really quite that strong. Let's see if we can. Well, I may as well go on. Anyway, this is just a global extension of this. This is what we use for the cover of our book. And you can see going back to Isaac Hell's fruit fly experiment, the first one that I showed, you can see the baroclinic waves marching across the southern hemisphere and across the oceanic sectors of the northern hemisphere. Let's see that one more time. And also at the same time, the tropics, we can see what we called back in 1968, it was referred to as popcorn cumulonimbus, but the more undifferentiated cloud systems over the tropical land masses. And the very obvious diurnal cycle. And the backdrop of that is this is the NDVI imagery over land, where you see the deserts and the jungles. So then, the next one, I just wanted to show an example of about a dozen videos that we have also from the NASA GEOS model, and they are various fields that have to do with aerosols and trace gases, carbon monoxide, carbon methane, and carbon dioxide. And we have I think it's at least there's something of order a dozen of them. And I'm going to just show one. This is carbon monoxide. It's early summer, just about the same season as we're in now, but back in, I read this, not sure I can read it. 2019. And we see some fires in, looks like it's in Alberta and Northwest Territories here. I think reminiscent of what you might have had here, had a couple of weeks ago here. And so we see the carbon monoxide, in this case, not coming down along the Rockies as it did this year, although hints of it. And then as we get later into the summer, the fires over Siberia, which are really numerous. I think this is one of the real expressions of climate change that I'm not sure, I certainly don't feel that I understand why there are so many more fires now. But it's wonderful to get an extent of their influence on the whole global climate from this and other videos. So then the next one I want to show you, I think of all the videos, I think this one is my favorite. And this is precipitable water. And the color scale at the bottom there is kind of complicated looking, but I think the thing that you need to know is that the bright reds and oranges are up around 50 millimeters of precipitable water. And they're actually in the tropics, the distribution of precipitable water is somewhat bimodal. There's a minimum around 45 to 50 millimeters. So the red and orange is above, they're in the upper lobe of the distribution, and then the cooler colors are in the lower lobe. And so we'll just let this go, and you can see how this field evolves slowly, like the vorticity field does in mid-latitudes, and that advection is playing a big role in shaping it. It really does have day-to-day coherence. And the convection, which is superimposed on it, it's on the gray-white scale. The convection is largely confined to the red zones, which are the really high precipitable water. So in a way, the precipitable water field controls the evolving distribution of the convection. Of course, this is the key element in this so-called shallow water, weak temperature gradient approximation, WTG approximation, that is used in a lot of the theoretical papers on the MJO and other tropical phenomena. So if you look along the edge of the tropics, in the subtropics, you can see that pieces of this high precipitable water air are continually getting torn off and entrained into frontal zones that go into mid-latitudes. Many of them are, let's see, many of these streamers that go into mid-latitudes are associated with the LC1 type of baroclinic waves. And the moisture and the convection in those tongues of warm, humid air tends to energize the baroclinic waves. And it's one of the ways that the tropics and the extratropics interactions in both directions roll.
Yeah, why doesn't the white of the outgoing long-wave radiation cover all the precipitable water?
Oh, it isn't just outgoing long wave radiation. It is clouds, and it is clouds as generated by the model from the vertical velocity field, and so it's white only where you would have cloud anvils like we're going to have here this afternoon. And even though it might, even though the OLR might be very high elsewhere, it'll be clear in this image.
But why isn't it white on top of the red where there's a lot of precipitable water?
Because it isn't raining there.
I see.
Yeah, it's all, the white is only where there's clouds.
Oh.
So it is the two fields superimposed. So that's why this is my favorite in a way. It was, or at least why I like it so much, is that you see so much because of these two superimposed fields.
Looks so viscous.
Yes, but that is the fact that it's controlled by advection, the field. And actually, this idea, I was talking with Brian Hoskins about this notion of the way the precipitable water field controls things, and he was reflecting on some papers that he wrote back in the 70s. Back then, they weren't aware of the role of precipitable water, but they were aware of the idea that it was not, that the temperature field in the tropics is not a prognostic variable consistent with the WTG approximation. It's really the vorticity field, which is more related to this, that is the field that gets advected. And the temperature field is just in thermal wind balance with that field. So perhaps that's enough of this for, at least for this seminar, and go ahead. So now one of a series of videos provided by Adrian Simmons and ECMWF, and this is assimilated data for I think this is the 2002 Southern Hemisphere stratospheric warming. And what we're seeing here is the water vapor mixing ratio on a very high potential temperature surface, up around 10 hectopascals or so. And so the purple is the driest. And this is air that has subsided in the core of the polar vortex. And we're seeing the vortex getting more or less normal in this early stages. And then I think just very, very soon here, we're going to see the growth of wave number 2 perturbation, very unusual in the Southern Hemisphere in September. That, it's starting to happen here. You see it splits the vortex into 2. And effectively, there no longer is an Antarctic polar vortex. And the streamers, Adrian likes this field the best of any of them. It's the most conservative, even more conservative than potential vorticity. And so you can see these streamers of it so nicely. So then for the stratosphere buffs, another animation. This is by Hamid Pavlovan, who just graduated from the University of Washington. He's a postdoc in Boulder here now with Joan Alexander and her group at Northwest Research Associates. So this is one of a series of movies or animations of the QBO that he made. And you can see the clock up at the top. And the field that we're looking at is the zonally average zonal wind field, which is the traditional field that is displayed for looking at the QBO. These are anomalies about the seasonally varying climatology. And you notice that the latitude scale is actually linear in sign of latitude, so that the tropics occupies half the globe. Instead of 30 degrees being a third of the way to the outside of the image, it's halfway. So that emphasizes the tropical features a little more. So we can see the successive blue or easterly and orange or westerly wind regimes slowly descending and being kind of like a flywheel in the global system. And then you see anomalies at high latitudes kind of alternating such that they're always in the winter hemisphere. And those are associated with sudden warmings, and they come and go But the QBO has this long memory. So it's quite a remarkable feature of the atmosphere. So there are animations for the total zonal wind field, for temperature, for vertical velocity as well. So I won't take too much time for that, and we'll go on. I just wanted to show you this one because it's a very simple one. It is just the climatology of sea level pressure, but varying with season. And so this is nothing but the climatology, but we're going to go through a couple of years. And so the orange colors here are the highs. You see this is January, I think we're looking at here. And we see the subtropical highs in both hemispheres. And then the blues are the low pressures. We see the Aleutian low, the Icelandic low in the northern hemisphere. And in the southern hemisphere, the circumpolar low is so intense, so much stronger than the ones in the northern hemisphere that it's rendered in purple. So we go through a year. I think this automatically goes through the year. And the thing that's interesting here that I had never fully recognized, I remember my colleagues Ed Sarachik saying, oh, the subtropical high in the South Pacific is so interesting. It's the same amplitude year-round. And it is true that the subtropical highs, all of them, are there year-round. But look at the difference between summer and winter. In the hemisphere where it's summer, the field is very lumpy, and those highs are essentially eddies. They're over the oceans, low pressure over land. It's very much a wave field around subtropical latitudes of the summer hemisphere. Whereas in the winter hemisphere, it's very much in the zonally average component is much more prominent. It's a little messy in the northern hemisphere because of the Siberian anticyclone, but you still, even there, you get that impression that in the winter, the high pressure stretches all the way across the land masses. There it is in the northern hemisphere, you see, as we go into winter. So I think even in some of the things we think we know very well, the animations can give us insights that we might not have been aware of. Then we have, I think there are about 100 of animations of the kind I'm going to show you now. And they're ones that I think they were still, we're still making them when Clara came in as a graduate student. We had files with drawers full of spools of microfilm, and each spool would have one of these animations on it, but it would be a series of still images. And these are in color, those were all contoured. But as we go around this, we're looking here actually at the 500 millibar height field on the 40 north latitude circle. And
So this is a teleconnection.
and these are we seeing, yes.
Yeah.
And this is the essence of Dave Gutzler's thesis. Let's see if I can do this again. So we see, at the beginning, we see mainly all the action is right near the reference grid point. But now we see the PNA pattern as it goes across the Pacific, and then we see the NAO as it goes across the Atlantic, and other weaker patterns at other latitude circles. So these are interesting to look at, and Brian Smoliak, one of my last students, produced a set of these for surface air temperature, for sea level pressure, for 500 millibar height, and one of them for a combination of those fields. So, so now I'm going to go to another part of the animations library, and it's kind of a coherent set of videos that are about gravity waves. And see if we're doing okay, Clara, in terms of time? Yeah.
That's 20 of, yep.
Okay. And we have till
I would say to the hour.
to the hour.
Yeah.
Good. So if you have questions, interrupt me, because we're not have much time at the end. This is from a paper by Nedelka Zagar. I think she spent some time here, at least in Boulder, I know, in the summers in recent years. These are spectra, wave number kinetic energy spectra for the this particular example is for the ERA interim model. And the similar ones exist for the latest, the ERA 5 reanalysis. And we're seeing the black spectrum is the total, where we see this extended -3 power law for zonal wave numbers ranging from baroclinic instability up as almost as high as the model goes. But when that is decomposed into Rossby waves and gravity waves, we see that the red and the blue, we see that the Rossby waves just are the overwhelming component at the wavelengths that we're accustomed to looking at. But when you get out to the high wave numbers, then the gravity wave contribution becomes appreciable, and in fact, it becomes dominant as you get out beyond wave number 50 here. And in ERA 5, that transition is more like wave number 30 or so. So that's all in way of just saying that gravity waves are important in the general circulation. So this animation is it's actually made by a private company in Japan, and the little spikes here are barograph traces from weather stations. And this is a particular morning, I guess it's an evening, January 15th. I forgot, I think it was 2 years ago. And oops. Yeah. Yep. Sorry. I'm doing something wrong. It's going, okay. So the red, these are anomalies. The data have been high pass filtered in time, so we're seeing the changes on scales of hours. And see that again. And so an abrupt pressure rise followed by a fall, followed by some further, much smaller, weaker wave-like perturbations going by. So to get a global view of this, here is water vapor imagery analyzed by Matt Barlow, and it has been treated in the same way, high pass filtered. The water vapor, essentially it is showing us mid-tropospheric temperature. That is what we are looking at. And there it is. That's the wave that went over Japan. This is the gravity wave from the Lamb wave from the Tonga eruption, which goes by in a matter of just about of the order of a day. And here's the antipodal point here on the right. And so we can see, oops. So you see the wave coming in and going out from the antipodal point and coming back and reverberating back and forth, back and forth. And here, meanwhile, back in Japan, about a day later, we see this. And this is the second round. We missed, they didn't show the one where it was going by the other way. But so this repetitive behavior is documented in the data. And same Njelka Zagar, her animation of it based on experiments with just a very simple model capturing the same behavior, the Lamb wave, back and forth. So this is all kind of esoteric because it is just one event. But this kind of behavior is going on all the time in the atmosphere in association with big thunderstorms. And so I'm going to show you Matt Barlow's image again. He blew this up, and you see this is the first frame after the eruption. You see the little pinpoint in the middle, that's Tonga. But if you look to the east, out towards the edge of the image, you will see, especially when I turn on the animation, you see a little circle of waves radiating out. That's a thunderstorm complex, and they're all over the place. So these are waves excited by deep convection, and also we're seeing these same slower internal gravity waves from the Tonga eruption. Long after the Lamb wave is gone, we're seeing waves continuing to radiate out. Those are much slower. They have a phase speed of 50 meters per second or so. And they're like the ones that are coming out from the convection. So here is NOAA SIMS imagery, thunderstorms over Australia, and a train of gravity waves coming out. This is water vapor imagery, like Matt Barlow's. Several events with the gravity waves coming out. And these can be traced, this animation goes for about a day. So they can be followed that far. They're moving about, some of them move around 50 meters per second, some more slowly. Now, an animation from the WRF model with 3-kilometer resolution, and it's initialized with a field that has already developed, but the high resolution is put in instantaneously. And by the time of this first frame, we're starting to see some gravity waves emanating from some of the islands at the eastern edge of the marine continent. And that's the diurnal cycle thunderstorms. And we'll watch those expand. And then as the animation goes on, we see successive generations of thunderstorms till it gets messier and messier. So they're all over the place. Only reason we don't see them in today's model is that we don't resolve them, but they're there. And of course, they're producing a lot of the effects that have to be parameterized in today's models. And then an animation by Hamid Pavlovon, the QBO guy. And this is in ERA 5 data. I don't have the time to explain how he did this, but these are actual ERA observations that have been filtered and composited where we can see these gravity waves, but they're not fully resolved because the reanalysis has about 25-kilometer resolution as opposed to the 3 in the previous one, but we can still see them. We're actually looking at the 50 millibar temperature field with reference to a burst of downwelling in the troposphere at T equals 0. So this sequence illustrates the effect of deep convection in generating gravity waves. And I just want to mention the other big source of gravity waves, of course, is orography. And here is a figure that produced in our department. Just it's not probably the best example, but it was the quickest thing that I could get a couple of months ago. A day with a front coming across the Pacific Northwest, and you can see the stationary pattern underneath the high clouds that's anchored to the terrain. And so these orographically induced waves are there all the time. And a still image from the book, on the left, we see the hemispheric field of vertical velocity. This is just annual mean 500 millibar vertical velocity. And you can see the around the edge, the band of orange, that's the subsidence in the Hadley, at the poleward side of the Hadley cell. And then the blue, prevalence of blue at higher latitudes, that's the ascent in the Ferrel cell. And we see planetary scale features. We can see the wet area upstream of Norway and British Columbia and state of Washington. But we look over land and the field is all wrinkled. And on the right, you see a blow up of the western United States. And if you use your imagination a little bit, you can see the Front Range there, along with the Olympics and the Cascades and other things. But they're not quite resolved at this level, but they have a signature there nonetheless. So the gravity waves, the stationary gravity waves are part of the climatology. And of course, if we looked at winter only, or if we looked at composite dates in winter, these features would be there and much stronger than they are. This is just the annual mean. It's just rather bland compared to what they look like in an instance in time. There's and then a university product here produced by Alison Wing and Ryan Abernathy. Convection, this is one of these models where it's just a tropical world, no rotation, no differential heating, but there's moisture. And so there's convection all the time, which you can see this continual bombardment. The colored field is sea surface temperature. It's just a mixed layer model for sea surface temperature. And notice how spontaneously the field is getting organized on the largest scale, and we're getting cool spots where the convection gets turned off and the convection gets squeezed into the warm regions. And so this is a aggregation of convection. So just showing how the animations really bring to life some of these phenomena that are under investigation. And I think this leads us to the last kind of frontier in this kind of imagery, which is looking at convection in more detail. And I'm just going to end with this image that was put together at NOAA as SIMS in Wisconsin. And it's the same case that we're looking at with different kinds of imagery. See the lightning, and this is visible. We're seeing gravity waves in the top of the convection radiating out within the anvils. We're seeing a larger scale, slower gravity waves going southward through Texas in this sequence. This color imagery is showing some of the same structure, but with information on the cloud top temperature. And this is a new kind of imagery called sandwich imagery, trying to have the best of both worlds, superimposing the color on the visible imagery so that you can see how high these cloud tops are. And so this, there's a wealth of really nice imagery that NOAA is producing all the time. The trouble is that most of it gets lost in effect or gets out of our reach because they don't keep, there's no archive for it that I'm aware of. Some of the better old ones get put on YouTube videos with a lot of junk and advertisements, and if you have all kinds of hours to spend on it, as I do now that I'm retired, you can retrieve a lot of it, and that's in fact what I did here. But I'm hoping that we could have a community resource that is well curated so that instructors could go in and find tailor-made, almost tailor-made videos for what they're talking about. I think the information is there, it's being produced all the time, but we need a way of getting it collected, of people who see something good to save it before it disappears or gets into the YouTube junk pile. And then perhaps as working collectively, and I think maybe even at some point UCAR might play a role here in making it available to the community. We've tried to do this on a small basis just to show how it might be done. But I think to do it right, you need to have more resources and more people and a real community effort. So I'd like to end with that. Thank you.
Okay, thank you, Mike. So fun to see. Any comments, questions for Mike?
That was beautiful. I think the reason there was not immediate comments is because we're stunned, actually. I think I could ask questions for the rest of the afternoon, but unfortunately, I didn't write any notes down, and but one thing toward the end, maybe I'll ask about, and that's those interesting gravity waves that first you showed from, was it a volcano or something?
Yes.
Okay, and then you showed how similar, only smaller things were from convection.
Right.
Are they forced by the vertical motions, or are they forced like a mountain? They block the flow.
Actually, you can see both kinds in some of this imagery. But the ones I was emphasizing are the ones that are forced by the convection and radiate out from the convection. But there are videos of Tonga where when this big anvil cloud forms, it's not it's not from moist convection. It's from the eruption itself. That cloud becomes an obstacle to the flow around it, and you can then see these orographic-like stationary waves, much, much shorter scale, along the upstream edge of that blockage. So they coexist.
I'm thinking of those rings that propagate out from the convection. How come they're so fast? It's just fast gravity waves?
Yeah. You're the expert at that yourself with the modes that you have studied all those years. Those are like lamb waves. They're, the fast group of them is going with the speed of sound, and you can see those in the reanalyses very well. In fact, we have some of the illustrations in our book inspired by your work, but showing it with the ERA5 reanalysis. These modes just turn up. All of them are there, and you see them very well in the two-sided spectra.
Well, I don't like to take all this time, but I would like to say that at the opening of Mike's talk, he talked about, I'm not sure if he said this specifically, but like 1968, when he presented a Hufmiller or longitude time diagram of clouds in the tropics. And I had the good fortune to be at that meeting. And I was sort of a rookie here, and my job was rapporteur of this meeting. So I watched every talk and I took notes. The only talk I remember was that one. And I'm telling you, it was a simple presentation, but nobody had ever thought about it. And just the very, again, the word stunned. I think we were all stunned to see these eastward or westward moving clouds by this Hufmiller diagram that he made. And he's been doing it for 55 years. So thanks for all.
Well, I think Herb Reel and others had written about those waves, many papers by that time. But I think it's being able to see things with your own eyes, and as researchers and as students, where you really learn and really satisfies that inherent curiosity that we all have.
Any other comments? I guess I'm really impressed by the breadth of phenomena and timescales, space scales and timescales that you've covered. And I think it's a rare person who, has that kind of breadth. So I thought that was very important. Oh, all right. One more comment from Raul, or
Why did Held call his model or whatever fruit fly? Was it fruit fly?
Well, it was just the simplest model, just like the fruit fly is the simplest biological organism.
exactly. Okay, well, thanks everyone. Let's thank Mike again. And that was a beautiful screen to see.